series of lectures that will be presented by Dr. Sauro Roshuchi on computational multiphysics. It's a great pleasure to introduce Sauro. Sauro got his education in Italy, and then he went to the École Polytechnique Fédérale de Lausanne in Switzerland, where he obtained his PhD. After that, he spent some time in various places in Germany, in Max Planck, and several other prominent laboratories around Europe. He was for a period of about 10 years working for IBM at the European Center for Scientific and Engineering Computation. And following that, he got an appointment at the National Center for Research in Italy, where he is currently a director of research. But also he has had visiting appointments in several places around the world, carrying out pioneering research in computational physics, mostly related to fluids. And we have been very lucky to have him as a frequent visitor, originally as a visiting scholar in the physics department at Harvard, and more recently as a fellow of the Initiative for Innovating Computing. So it's a wonderful pleasure that Sauro agreed to give this series of lectures. It's related to his most recent work on multi-scale physics, multi-scale approaches to computational problems. And it spans a wide variety of physical systems, and I'm very excited and very interested to follow his talk. So he will give a series of 4 lectures, 2 hours each, starting today and going through Tuesday of next week. There's a small change in the scheduling that he wants to inform everybody about.
If I can track it, I think, thank you, Tim. On March 17, which is next Monday, the lectures will be in Jefferson 356. And maybe you can, okay. So thanks very much, Tim, for, can you hear me? I think so, yeah. Thank you very much, Tim, for the introduction. In fact, it is really for me to thank Tim and the IIC for this very nice opportunity. With Tim, we've been working for a long time, and it has always been very profitable for the scientific point of view, and even more so from the human one. So I'm really very grateful to him and very happy to be here today. This is an experiment, so I wish and I hope that we will all somehow interact in such a way to make it better and better as we move in time to the various lectures. And the other thing I should say right away, that these lectures are not intended to the specialist, but essentially they are intended to convey general ideas on the way you tackle multi-physics complex problem using multi-scale, multi-physics, and multi-level techniques. As you all know, you probably all know that when you are facing a really complex problem, there are hardly any general solution, and the success really depends on details. And during this lecture, it will not be you should not expect that we can go down deep into detail, but just expose general guidelines so that I hope I can stimulate your fantasy, and maybe we can offline discuss your own research project and see whether these general guidelines can do some good to it. Okay, so the plan of the lecture is, so today will be, the first lecture will be almost philosophical, just to give the general motivation behind these methodologies. And in the second lecture, today, I will give some basic notion of computational physics and actually those who are relevant to multiphysics. Tomorrow I will be a little bit more formal, not much, but still expose some of the machinery, mathematical structures which are needed to solve multi-scale problems. And then we will see some little examples, which I picked up from a paper I should have referred you by Weinan, He, and co-workers. I can give you the references. The example covered gas kinetics, which is autocoupled kinetic theory and ideal fluid dynamics. The second example is again on fluids, but dense fluids. So it will involve molecular dynamics and non-ideal fluid dynamics. And next week, we will go into some up-to-date applications and biopolymer translocation, which is precisely the project we are carrying on here with Tim and since a few years, and Simona Melchiona, who is possibly sitting in the audience. And the second application will be, again, another hardcore. These are more seminar than lecture, on the way we use multi-scale ideas to tackle a very tough problem, which is fluid turbulence. And I will conclude with an application which, in fact, probably should be for Tim to present, because the fracture dynamics is something I've not really been actively involved in, but I think is the only example, as far as I know, where you couple 3 different levels of representation. So I think that has to be there in a series like this. But if you have R questions, they are not for me, they are for Tim. Okay, we are talking computational physics, so I hope you will not drag into this kind of negative loop. I don't know whether this is, it's an interesting joke. I hope we can use computer but still stand in this part of the parabola. Okay, fair enough. Just give me 1 second to start with. So let's start with some general notion. Why do we need or we want to do multi-scale physics at all? And the reason is, as I said, I will be a little bit philosophical in the beginning, but I think it doesn't hurt. So we know that as a scientist, our goal is to make sense of the world around us. And the world around us is pretty large, it's pretty big. Typically, I would say there is a kind of bias in science and outside science that the most challenging frontiers of science are in the extremes. So the extremely large, like, cosmology, or the extremely small, subnuclear physics, string theory, and even below that. But we also know that over the recent years, there is increasing focus into the middle ground, and where, in fact, most of top complexity lives. And in fact, there is more and more focus into disciplines which until recently were considered just too complicated to be amenable to quantitative analysis. So my lecture will be basically man-centered. We will not cover parsecs or Fermi or kind of scales, although in principle the techniques can be applied to these scales as well. But I will be basically focused from the meter to down to the nanometer. That's because it's my own experience. But again, I hope that some of the ideas which I'm going to show, I'm sure, in fact, they would apply to astrophysics. And I guess, although I'm not so, astrophysics I'm pretty positive. But I guess they could be applied to quantum field theory as well. But that's a bold statement. It has to be verified. So, but let's expand the whole picture. So, how does science proceed, and how did science proceed so far to make sense of a huge building? We live in a building which is basically made of, some 60 floors, and each floor is 10 times bigger than the previous one. So if I'm not mistaken, the radius of the universe is about 10 to 26 meters, and that's the largest, that's the size of the bubble, so to say, and we go from that distance all the way down to length scales which are of the order of the Planck length. So the smallest length where apparently space-time itself lose its meanings is of the order of 10 to minus 35 meters. So there are 60 levels into this description, and how do we go about the problem of describing the universe? So as you all know, a very successful formula, a very successful approach was the reductionism, which is to say, going back to my fellow Romans, divide et impera, so divide and conquer. You have a big problem, you cut it in pieces, you try to solve the single pieces, and then hopefully you have a recipe to glue them together once you've solved one at a time. So the idea is to go down deep, okay? That's the typical path of, say, elementary particle physics. And once you know what happens at that floor, apparently it's a trivial task to re-emerge and describe, say, humans in terms of quarks. Of course, that would be foolish, and what happens is that you segregate each of these levels and you develop methodologies which are suited to this level. As you try to isolate the levels as much as you can so that you make your problem simpler, and you can isolate it and focus on the details of each of these levels. So as you all know, this is the dream of Laplace, was to say, if I could know, at that time they were talking about mechanics, if I could have a powerful enough computer, I could compute the trajectory of all atoms and I would know anything that needs to be known. Nowadays we know that things are not so simple, and essentially because of three reasons, if I can summarize. Why is the universe so mysterious and fascinating as it is? Well, of course, this is itself a simplification, but I think we can isolate three basic elements. In the first place, the universe is huge. Huge means that there are many degrees of freedom. I think the ballpark estimate is that there are about 10 to the 80 elementary particles, which I think makes for the density of about 1 proton per cubic meter. So this is a large number of degrees of freedom, but I think even more to the point, the universe is broad. Broad means that the ratio between the largest scale and the smallest one is wide. We have about 60 decades to describe, okay? And it is nonlinear. Nonlinear, as we will see many times, means that there is energy and information transfer across these levels. So even though reductionism, wisely so, tries to isolate level by level, the fact remains that these levels are not segregated. And for certain systems, especially the complex system we are interested in, this cross-correlation simply cannot be neglected. So this is, if you want, the message of the science of nonlinear system, which develops in the early 60s. And by now, we know how important, in fact, the nonlinearity is. And in fact, I would say nonlinearity is really the ultimate driver of complexity. Do I need to remind you why the reductionism, which is very powerful, as some Achilles heels, I think you all heard about the idea of the butterfly effect. In other words, it's computing the most elementary, let me call them trajectories, implies that you have to solve very many equations, okay, of the order of, in principle, 10 to the 80. And there are fundamental reasons why, in fact, this is not possible, because if you have a nonlinear system, the smallest uncertainty on the initial condition will develop into dynamic instability, so you cannot, the predictability horizon is very limited, and you all know the famous paradox that if a butterfly beats his wing on the Antille in Cuba, you can have an hurricane in Florida, which is an exaggeration, but conveys the idea that it is just not possible to think that you can integrate as many equations as you want. There are practical limits and conceptual limits. A second effect, which is less known but no less important, is what is called Nile effect. Nile effect comes from Dan Frankel. He has a book in molecular dynamics. And the fact is the following. Suppose that you have all the information regarding 10 to the 80 particles, and all you have to do is supposed to just compute an average quantity, which means summing up of the order of 10 to the 20, a number of Avogadro. Suppose you have 10 to the 23 atoms in a cube, and you want to just compute the average temperature. So you have to sum up the energy of all these atoms. It so happens that this looks like a trivial operation, but it is not, because in complex systems, very often there are some rare events which contribute most of the weight to this average, even though there are very few. So you have probability distribution function, which develops so-called fat tails, and take an event like this, it is a very rare event, this event will contribute a lot to the average, and if you happen to miss it, you will miss substantial amount of the macroscopic response, even though this is a very single and very unlikely event, but very energetic. So the Nile effect, it means that you have the Nile in the African territory is a very, very sneaky structure, but it carries a very important weight. And if you are trying to measure averages, in fact, you should be able to track these rare events, which is only possible if you have an infinite amount of resolution. So the reductionistic program, in a way, it's an ideal program, which has very stringent limitation in practice. And this limitation become apparent when you deal with complex system. So I think that this, I don't need to spend much time about it. Short-term horizon and self-organization, etc., etc. But the crucial point is our nonlinearity and rare events. Now, for the sequel, I'm going to concentrate, as I said before, on a much shorter stretch of the hierarchy, and these are the people. Basically, we're going from, say, the quantum world, so 1 Armstrong, up to meters and upward, but essentially from meters to nanometers. I don't know, a good test is, do you know these people, of course? I think Schrödinger, Newton, and Boltzmann are pretty well known. Here, I think it's tougher. This is Navier-Stokes, which are responsible for one of the most important practical equations, the equation which describes fluids. And I think this is Stokes and this is Navier, but I always mix them up. So it would be interesting for you to, this will be assignment number 1, with Navier, with Stokes. My guess is Stokes and Navier, but I might be wrong. Now, it would be a full course to explain how to solve these equations. I only want to remind the simple fact that here we are dealing with continuum fields, and here we are dealing with probability distribution functions. So there is a change in the mathematical representation. Okay? And this will be crucial for multiscale techniques. Multiscale techniques means that you have to invent swift ways and computational and mathematical ways to go from one level to another in a seamless fashion. Okay? So we have fields, density, pressure, velocity. We have probability distribution function. For those of you who took class in statistical mechanics, this is obvious. Otherwise, I will have to explain a little bit during the practical examples. Newton equation you all know. Okay, so this is specified in terms of molecular position and velocity. And quantum wave functions, we are back again to fields, although these fields are applying to a much shorter scale. So essentially, multi-scale techniques will always have to swap between continuum and discrete representations. Okay? And you need mathematical tools to do that. Now, statistical mechanics is, in fact, the conceptual framework which is needed to formulate multiphysics and multiscale problems. So, and statistical mechanics in its textbook version tells you that essentially in going from here to here, you have to remove a lot of information. As I said before, it wouldn't make sense to design a car by integrating the equation of motion for the atoms. Okay? That would be totally useless, unwieldy. And so you are, in fact, developing at each level the proper mathematical description. The general idea is that details which are living at this level will be, in fact, washed out as you progress toward the macroscopic world. And the idea is that the macroscopic world should have many less degrees of freedom. One thing which is not very often told in textbooks is that, yes, you have less degrees of freedom. But by the time you put these degrees of freedom into a computer, the equation you have to solve are sometimes so complicated that it becomes arguable whether it's worthwhile to go to the coarse grain level instead of solving equation at the lower lying level. And that we will see example of this. But in general, the trend is here I have many relatively simple, let's take Newton versus Navier-Stokes. Here I have now very many relatively simple equations to solve. Here I have just 1 or 2 equations to solve. But these 1 or 2 equations can be very, very tough. So one has to keep open mind and decide, in fact, which level is most suited to his problem. For instance, very recently, or for the last 10 years, we have, as a community, one has discovered that it might be much wiser to solve fluid problems using, in fact, kinetic formalism, which in principle contains a lot of redundant information. So, yeah.
What you didn't tell us what is BBGKY. They're not the initials of those guys you were showing us.
Oh, that's right. I'm sorry. That's too technical. Q means quantum. BBGKY is very technical. It's Born, Bogolyubov, Green, Kirchhoff, Ivan. None of them is here. So that's an inconsistency. I'm sorry. Just I have a minus. I have to correct that. Now, this is very technical. Who has heard about BBGKY in this audience, apart from my friend Bruce? And well, that's very technical. I mean, and the reason why I put this person is because apart from Navier and Stokes, I think all the others are universally known. Navier-Stokes probably not. So this is a very technical word. I'm sorry about that. I will correct. So, but the main point, again, general guideline, is that one should keep an open mind in terms when they as a student myself, I think it's still true for you, they tell you, okay, you have a fluid dynamic problem to solve, you immediately identify this with Navier-Stokes. No, please don't do that. Keep your mind open, and there are ways of working through all levels of this hierarchy. And I'm very pleased to see my friend Kim Molvig sitting in the audience. I don't wear my glasses, but I think it's you. And Kim, I think I'm very happy to give him credit, is one of, in fact, the inventor of a technique which allows you to solve fluid problems using this level of description, although in a very fancy and ingenious way. So here in Boston, we have, in fact, living example of this idea of keeping your eyes open and try to work through the hierarchy in a very flexible way. Now, but on the other hand, on the textbook, we learn a different story. We learn that if you want, say, for instance, to describe a structure like an airplane, well, in principle, as what the team does, for instance, if there are fractures in the planes which can be tracked back to the way bones are broken. So in principle, in statistical mechanics, you start from the most elementary level, which is the electrons. You go to atoms. You go to some intermediate description. And the idea is multi-scale model is a transfer information from the finer to the higher scales. This is only partially true. That's the sweet part of the story, because this conveys this is not wrong, but it conveys the idea that the flow is one way, from micro to macro, just like reductionism. It is not wrong, but it's not complete either. Because if you take a complex system, okay, let me call it, just for the sake of fun, there are well-behaved systems in which, in fact, they abide by the hierarchy. So you have the de Broglie length, and you go atomic, and then you go to molecular dynamics, the typical interaction radius. You go to the mean free path, which is something related to the statistics of the particle interaction. So this is one angstrom, this is maybe a nanometer, this is maybe hundreds of nanometers. Then you go to macroscopic field, and I will spend a lot of time telling you what the coherence length of a macroscopic field is, and then you go all the way up to the global size of your problem. In a well-behaved statistical mechanical environment, this is one-way flow, and there is not much to discuss. A lot of details here, many less details here. But as we will see, for many real-life problems, it doesn't work that way. There is kind of maverick behavior, bad behavior, where in fact there are takeovers in this hierarchy, and the exchange of information is by no means one way, because the upper line level is feeding back into the microscopic level. So it's always a kind of dialogue between the macro scale and the micro scale. And just because of this dialogue, one of the milestones of statistical mechanics, which is the central theorem. Central theorem tells that if you take a system big enough, fluctuation will die out, and you will have a simpler description of your system. So the fluctuation regress. If there is a two-way flow into this hierarchy, it is not true by no means that fluctuation would regress. Very often fluctuation develop, persist, and invade the system. And this is not a framework which you can describe with the standard tools of statistical mechanics. What I'm referring to is what we might call extreme statistic, non-Gaussian, where, in fact, fluctuation become relevant and sometimes dominated. Examples. Turbulence. I will use turbulence very much, just because I'm rather familiar with it. In a turbulent flow, for instance, like this is a turbulent jet. The simple idea is that the turbulent flow is a kind of mixture, is a gas, where you have large-scale structures like this one, and smaller scale structure. And the idea is that the small eddies are just like satellites. Big structures take the sun and the satellite. A large eddy is the sun, and the small structures are satellites, which are just swept, advected by the large eddies. And the effect of the small eddies on the large one is just to collide and just generate a sort of Brownian motion. It's an analogy with kinetic theory. But it doesn't work that way. I mean, qualitatively fine, but if you try to do quantitative calculation based on this analogy, you fail. And the reason why you fail is because there is an infinite, in fact, there is a continuum spectrum of eddies, and it is never the case that larger it is, the distinction between advection and diffusion becomes fuzzy and depends on the scale you are considering. The result is, again, that you cannot describe this by simple Brownian motion, and you develop a situation where, in fact, there are bursts. We all know that turbulent flows are bursting, they are intermittent, and these are the rare events I was referring to. So that's a case in which there is continuous information between, exchange of information between the small level and the small scale and the large scale, and this is a continuous dialogue. But just simpler example, persistent details. I just learned recently, there is a nice paper on Nature, that the way you take a drop and you let it go into, you just throw the liquid drop into the water, and the drop can either go down with a little blip, no noise, this is a noise signal, or it can make a lot of noise, just splash through the water as you throw it, and this is a noise signal. The difference between this and this, which is substantial, can be traced down to very minor details on the rugosity of this droplet and the way, in fact, the molecules into the droplet interact with the molecules of the surface. So very minor detail which do not wash out at all when you do your experiment. So that's a case of a detail which is persistent.
So what is this exactly? It's a drop of what?
It's a drop of liquid, and you let it go into another liquid. And they observed that, in fact, there is a critical speed which relates to the atomic properties of interaction between the molecules, such that below the critical speed, you go down silent. And just above the critical speed, you splash. And that really traces back to the atomistic interactions.
And the two substances are not soluble? I mean, the drop is not soluble?
No.
But it's not a solid drop.
No. It's a liquid. Okay. This you know, because this is your work. As I was mentioned before, the way, in fact, the crash of an airplane can be tracked back to the bond breaking, which takes place at the level of atoms, and Tim and his collaborator, they have developed a beautiful, I think the only one multi-scale application involving quantum mechanics, molecular dynamics, and continuum theory. That will be my last lecture, and I hope Tim is around because I'm not the expert. Another example, I mean, just to, again, keep your mind open and on the idea that statistical mechanics is not just about removing information. That is really not true. I call it inflationary details. We all know, and that has been done across the river, actually, Bose-Einstein condensation. What is Bose-Einstein condensation? Well, it's basically the de Broglie length, so atomic length, which becomes macroscopic. If you cool down the gas fast enough, the de Broglie length, which is inversely proportional to the temperature, will become macroscopic before the system has time to crystallize, where crystallization will be the normal statistical mechanic path. If you cool down fast enough, you just completely overturn the hierarchy. Remember what I was showing you. Oops, too much. So basically, you are going from year to year, puff, in a single swoop. You're just jumping across all the intermediate level just because you're constraining the system from the outside. You're cooling down so fast that there is no time for the system to go slowly and peacefully along the hierarchy. So you see how many interesting things happens outside the standard path of statistical mechanics. And biology, I don't need to tell you in the first place because I'm not an expert, but biology is basically the paradigm of self-assembly details, and here there is even the notion of developing a function. Okay? So not only the small scales do not regress, they build up and they construct functional system, which is a mystery in itself, and I think that's one of the most fascinating frontiers of complex systems. So bottom line, when do we need multi-scale level physics modeling? I would say essentially when the cross-scale connection cannot be disentangled. This is a take-home message for sure. Whatever this means. I gave you just a few qualitative examples where details do not recede, the detail persist, or even invade the system and conquer the system. Second general guideline, which I already mentioned. So the bottom up, so the macroscopic persistence, sometimes even self-assembly, And that's very important. There is continuous feedback from the macroscopic level into the microscopic one, and we will see that one of the possible mechanisms is the energy cascading from large structure to small structure, which is the typical mechanism of turbulence. Now, in this context, there is, of course, the major problem is, again, how to connect microscopic world with the macroscopic world. And, of course, people could do a lot of very useful and very important job prior to multiscale, of course. And how did they do that? I think the main glory is on constitutive relation. Constitutive relation means that you can essentially boil down all the microscopic physics and lump them into a few representative parameters. Let me, okay. I think you are all familiar with the Fick's law. Fick's law essentially means that the flux of a given quantity is proportional to the gradient, okay? And that's the way equilibrium, thermodynamic equilibrium is established. You have a cold fluid and a hot fluid. The hot fluid is transferring heat to the cold one, and the two get imbalanced. So there is a heat flux which is proportional to the gradient of the temperature. That's, again, something which holds only near equilibrium. But when you are facing with wild systems, far from equilibrium, this simple proportionality between fluxes and gradients no longer hold. So the constitutive relation is something that is useful, but only provided you are close enough to equilibrium. And for instance, in the case of turbulence, they are not so useful. So you have essentially to use multi-scale level in physics whenever the constitutive relations are either too complicated to be practical, or maybe they don't even exist. So if one goes into the review paper I was mentioned to you by Weinan and collaborators, they classify multi-scale problems as follows. So they say the class A, so where a microscopic model breaks down. For instance, in microfluids, sometimes the continuum description of the fluid is not appropriate, and you should acknowledge the molecular identities. And typical examples are in material science, when you have isolated defects, cracks, and content lines, situation where continuum elasticity would not hold. Class B is where the microscopic model does not break down, but is too unwieldy, it's unpractical to be computed. And there are many examples in complex fluid. Class C is just A plus B. And class D is the problem like turbulence, where you have self-similar, you have energy transfer at all scales. So Weinan mentioned critical phenomena, fractals, and turbulence. These are possibly the toughest problem in a certain respect. So I'm not that interested in going in detail into this taxonomy. I would rather show you some examples of multi-scale, multi-physics, and multi-level situations. Okay. Again, turbulence. So what is, let me get a little bit more detail on turbulence. So why are turbulent flow so complex and hard to compute? Is because this is the energy spectrum. So you take a fluid and you inject energy on the large scale. So this is the wave numbers, which means that the left side is associated with, you can take, say, if this is a car, this will be the size of the car. A car moving, okay. The energy is basically, or you can take, say, a chemical reactor where you have some propeller. So that's typically the scale of the global problem. So what happens is that you inject energy into large degrees of freedom, and then due to the structure of the equation, these structures are unstable. So they break down. Here I should have depicted maybe two of them. So they break down in smaller structures, and the smaller structures are still unstable. They break down, they generate smaller and smaller childs. And the interesting thing is that in this chain, energy is perfectly conserved. Well, not perfectly, but almost perfectly conserved. So from year to year, the system is conservative. No notion of dissipation, I mean, very, very minor. And until you come to the point where the eddies are so small that indeed they cannot keep their shape, they cannot be coherent anymore, and so they subside, they just like, imagine they break down and then the molecular world shows up. Interestingly enough, this transition is very, very sudden. The technical word for this is that turbulence is critically damped. It means that as soon as you reach the critical size for the eddy disappears. It just takes one eddy turnover time. Eddy turnover time is the time it takes to take a fluid, okay, a vortex. I should have something like this. By the time the particle makes one tour around the eddy, it's gone. It doesn't take 100 or 1,000, 1 or 2. That's critical damping, which means that here dissipation takes over, and the fluid, in fact, dissipates into it, basically. Now, this spectrum is broad. I was mentioning the universe. The universe has 60 decays, far too many for any computer. Turbulence has 6 decades, typically. Still, as we will see, far too much for our present-day computers and any foreseeable computer. But besides being broad, the real problem is that it's gapless. Because suppose it's that broad, but you have, like in atomic spectra, you have a lot of energy here, you have a lot of energy here, and less energy here. But if these bands were separated, you could treat them separately. The reductionistic approach. And they would not talk too much to each other. That's not the case here at all. I mean, here everything talks to everything. So gaplessness, if I can use this horrible word, I think it doesn't exist in English. The fact that the spectrum is continuous is the real reason why turbulence is so hard to predict. That's the maverick kind of behavior. Okay? And if you go in books on linear mechanics, they always tell you that if you have continuous spectra, you lose space and time coherence at the time. So that's exactly what's going on here.
Why do you have this kind of gapless? Where does it arise from?
That it arises, I mean, from the fact, for the case of turbulence, arises from the fact that, oh, actually, one thing I forgot to say. I have the lecture plan, but I would very much prefer to interact. So I don't need to present all the material I prepare. I much prefer to have questions and discuss them on a free schedule. Where it comes from is mathematically turbulence as a the Navier-Stokes equation have a term like this. And this term means that the fluid transports its own momentum. This is the fluid momentum. Take a piece of fluid, okay, and it has mass, momentum, temperature. And U grad is a convection. Now, if you take this term, beside the mathematical representation, this is the terms which is such, if you take a wave like this, and this is a velocity field, the particles which are ahead move faster. And so essentially, the particles which are behind move faster than the particles which are ahead. So as a result, the next configuration will be like this. So the wave is steepening. Steepening means that the energy is going into scales which are smaller and smaller. And this is a continuum process. It doesn't go in jumps. So that's why, in fact, you fill up the spectrum from the largest to the smallest scale until the front is so thin that dissipation takes over. Because the eddy it takes energy to keep coherence. It's like in quantum mechanics, if you want. Okay? And at this level, there is not enough energy to support coherent motion, and so you subside to molecular individualism, as it is called. But the reason why, the ultimate reason why a fluid has a continuous spectrum, because the fluid transports its own momentum. And I think you all know that in mathematical terms, if you take a Fourier transform of this, you mix up all the energy. You have beatings and resonances. So this is a nonlinear structure. Quite general, I would say. That applies to almost any classical field theory. Any question? Yeah, please go ahead, because otherwise it's boring.
Your example, you said that the particles in front are slower.
Oh, because that's the typical case when you have same. Well, yeah, exactly.
Why is it typical? I mean, in turbulence.
Oh, no. That's no. You're right. I mean, I'm not saying that this is typical. This is an easy to grasp example of why energy goes from large to small scales. Okay. On a more on a deeper level, I would say that the deep reason is when you have this kind of non-linearity, so that you are transporting your own momentum. So You can analyze this, and you will see that the large eddies which are beyond larger than a critical size, in fact, are unstable. So this is a driver of instability. It's a more mathematical, I'm sorry, kind of. And this is just an example. What happens in turbulence is that the eddies break down. I mean, you can see that in movies, and I think turbulence is a gold mine for photographers and
Just ask, this is temperature independent?
Oh, not really. Temperature it's important if you consider compressible fluids, like in astrophysics or gas dynamics. This kind of spectrum, which is typical of incompressible fluids, where I don't think temperature is a major player. That exponent and this type of mechanism really does not depend on temperature. If you have temperature, things, of course, are much more complicated.
But so it was my impression that once you get to the inertial range, once you get to the -5/3, then there is some things you can do, Kolmogorov theory of turbulence. But it seems like in wall-bounded flows, then the range of scales just to get to where you have universality is so vast, then by using sort of simple, straightforward computational tools, you can't even resolve the scales that precede the inertial.
You can or you can't?
You cannot, because there's no computational power. Just if the Reynolds number is large enough and you have a wall-bounded flow, then just to get to the beginning of the inertial spectrum is in itself.
Oh yeah, sure.
So my question is sort of running ahead whether there's application of multi-scale theory.
Oh, yes. Sorry. Certainly, I mean, there are many recipes to... I think the most popular strategy is called large eddy simulation, which is a way, in fact, of simulating only the largest... I mean, this is getting really very technical, but I have some slides later on that.
Right, but I was also... I was under the impression that large eddy simulation begins where you hit the negative, essentially. You need sort of a point in the universality.
Okay. Well, universality, you mean universal range is this, the blue one, where you have this exponent. Universality, for those who are not in turbulence, means that this exponent really doesn't know about the initial and boundary condition. Geometry is forgotten. Okay? So that's what universality means. In bounded flows, this is a question. I mean, in bounded flows, this can only be true far away from the boundary, if this is your question. So the question is how much I can rely upon the assumption of universality. Is that your question? Well, what happens in practice is that you have a certain compute... Sorry?
Can I make a comment?
Sure, Kim.
Okay, I thought he was talking about the range of scales between the largest scale and somewhere well into the inertial range.
So tell me where do I have to put my point? Here, you mean?
In many cases where there's only a couple decades there, and that is affordable computation.
You mean from here, say, to here?
Yeah, to some
Sure.
point well in the inertial range to the maximum scale of the problem is typically only a couple of decades.
Yes.
And that's resolvable in 3D with modern computational techniques.
Yeah, sure. But, I mean, how about the rest of the spectrum?
Well, I was just trying to get you to that point. I thought that was his concern, was you couldn't get to the inertial range.
No, that's right. Normally, you don't get to the inertial range, you get somewhere in between. And
Well, I mean, my point was that if you allow the Reynolds number to increase very large, then even getting to the beginning of the inertial
I
range.
see what you mean.
Right, and I was saying that's not so much the question
No,
on Reynolds
no.
number as the geometric details of the problem and how many scales you have before you settle into the inertial range. And
Yes,
I
yes.
don't know why you thought that was not affordable.
No. Normally getting to the inertial range is affordable. The difficult part is, typically you would have your computer resolution up to something like this. You would resolve, 3-4 decades, and the rest you have to model. But getting into the inertial range, as far as I know, is not a problem. You can back me up, Kim, but
No, I don't consider that a problem. I mean, you could make a
No.
very complicated geometric system where there might be 3 or 4 decades and big scale down to the inertial range. That's not fair.
I know we should perhaps ask,
Wall-bounded flows don't put you in that.
is there I don't know whether in astrophysics, what is the largest?
In astrophysics, this is a problem, and what people do is they know density resolution, so the dynamic range in simulation in density is terrible. And so what you do is, because you have this gigantic
But,
range.
and
yeah.
what is the largest
Yeah, I was thinking of
Reynolds
something more
number
like an
we have?
airplane or an automobile, not a star.
Sorry, sorry.
What is the question for everybody? I mean, I was told by friends that generally the Reynolds number, which I have not introduced that, but it's a measure of the breadth of the width of the spectrum, is of the order 10 to 10. A car is 10 to 7. What do you have in astrophysics? You don't go to 10 to 30. Is that
No,
right?
not that.
10 to 12.
Yeah.
Okay. In cars, I think airplane is 10 to 8. I have a lot of slides on that, so I think we can but I mean, we will have more to say about that. But I never thought, in fact, in terms of having a Reynolds number so high that I don't even make it to the inertial range. So it's an interesting comment. Normally, the troubles are on the high end of the spectrum, but we'll come back on that later. And factually, that's exactly where we are. In fact, now that's very general. I mean, I will use turbulence as an example, but really this applies to each time you need to couple a nonlinear field theory to an atomistic or particle model. The question is, what is the coherent length, and how do I measure? How do I estimate the coherence length? So in the first place, what is the coherence length? Well, as the name suggests, is the smallest length below which the continuous representation fails. The coherence length, don't be fooled, is not the atomistic size. It's generally larger than that. It takes several atoms to build up a vortex. I'm not saying it takes an Avogadro number, no, but it takes perhaps 1,000, 10,000, 100,000. So the coherence length is usually, typically, larger than the microscopic scale. So here we have three scales. Your global object, say a car, an airplane, whatever, meters. You have the microscopic scale, and let's assume that this is atomic size, okay? And you have something in between. Now, how do you estimate this something between? Please appreciate that you have to know that if you are designing a multi-scale application, because the assumption is that you want to use continuum equations as far as you can, because even though this is a kind of prejudice, the continuum equation, the macroscopic model, will be cheaper. So you're trying to compute in the red stripe as much as you can, and confine the microscopic calculation, which is green here, to make it smaller and smaller. But you have to know the physical information. So up to which scale does the continuum representation make sense? This is not trivial. This is not the atomic size. You need theories, you need sometimes complicated theories, sometimes more frequently so dimensional theories, but essentially let me anticipate, and please suspend criticism so far, that there is a relatively simple expression, which is a scaling expression for the coherence length versus the global size of your problem. And this little g is basically the coupling strength of the theory. In fluid dynamics, it will be turbulence. In chemistry, it's called Damm-Köhler, and you name it, every field has its own coupling strength. It will be basically the prefactor of nonlinear interactions. And I can anticipate that g is basically a ratio of timescales. We will see, in fact, in more detail. So generally, what happens is that the coherence length scales like g minus some power, which is a power between 0 and 1. Now, you can, just for the sake of simplicity, recast the coherence length in this sort of interpolation. So the microscopic length to some power a times the macroscopic length times to the power 1 minus a. And you immediately realize that this A is a measure, we could call it the penetration index. It's a measure of the penetrating power of continuum. Penetrating means that if a continuum theory is very penetrating, means that it can bring the coherence length down and down deep to the microscopic level. And how much, the specific value of the penetration index depends on the physics. I can anticipate, it will be easy to show that in the case of reaction diffusion, flames, the penetration index is 1.5, is diffusion, basically. Diffusion against reaction, so you're not surprised to see factor 2. And so that means that you have a domain, say a reactor, a big reactor, of chemical reactor 1 meter, and again, we assume that the microscopic scale is 1 angstrom. The continuous theory will penetrate, will just stop halfway. So if I have a meter, I will have a valuable, I mean, the continued representation will hold up to some 10 of microns, which is just sitting in between, geometrically, in between the two extreme scales. Turbulence is more penetrating. Generally, when A grows closer to 1, it means that your continuous theory is strong, is a strong interaction. So weak interaction means 0 means that if A is 0, it means the coherence length is just L. So there is penetration 0. There is no energy transfer. So this is a weak interaction. Actually, this is no interaction. A equal 1 is an extreme case. I don't know of any nonlinear field theory with A equal 1, but maybe it's just my ignorance. But A equal 1 means that the coherence length is just matching the microscopic scale. So you have enough energies to push it down, all the way down to the atoms. I don't know of any field theory who does that, but it would be interesting to know. But I know for sure that turbulence has a penetration exponent 3/4, which means that instead of going down to 10 microns, you go to 30 nanometers. So you sometimes find papers where the question is asked, how far can I go with the continuum? This does not really depend on the size of atoms themselves. It's a problem-dependent question. It depends on the interaction. It depends on which continuum theory you are considering. If it is turbulence, you can be assured that you can use the continuum representation up to 30 nanometers. Then, of course, there are other considerations. You should ask whether you have enough molecules, but you do have enough molecules. In 30 nanometers cube, you have 30 molecules of water in a nanometer, so you have tens of thousand molecules. So you can safely use Navier-Stokes equation up to 30 nanometers, which is a kind of surprising statement, but that's consistent. But the important notion, again, general guidelines, is that you have to know the coherence length before you start to set up your multi-scale application. If you don't know that, you're going to, I mean, you can miss. Yes?
What about critical fraction?
I don't know. I really, we should look into that. It really depends on the equations.
That might be a case where A is close to 1, and you really need to go all the way.
We should analyze the equation of nonlinear elasticity. Yes?
We have an expert here in the audience on that.
Pardon?
We have an expert in the audience, so
Ah.
should talk to Katerina.
Katerina. You are Katerina. We are supposed to meet later. Okay, good. Hi.
Okay. What about alpha? Is there a relationship between alpha and A?
There is a relation, but I'm red-faced. I think the relation is trivial. Each time I try to work out, I got a mess. So I prefer not to enter that, but they are certainly related. I can tell you that in the case of turbulence, this is minus 3/4. So in the case of turbulence, the alpha is equal A, but I'm not waterproof that this is generally the case, so I prefer to keep them separate, but they are certainly related, yes. The important point is that they depend on the application, right? So I don't know. It would be interesting to see what nonlinear elasticity does. Another general remark, I mean, is that for strong interactions, so as A gets close to 1, generally the field theory develops singular structures. I will show you in a moment that the fact that you have 3/4 means that the gradient in a turbulent fields are singular in principle. Of course, there is always an ultraviolet cutoff, but within this range of scales, if you try to compute the gradient of the velocity field, it would turn out that, strictly speaking, the gradient is singular. It's not defined. So this nonlinear field theory is generating, in fact, very localized features. And that's why the computation is difficult, because nature is nitty. It puts all the... There is another very general message. I should have made it much more clear. When I...
Before you go on, I
Yeah.
have another question. So G is a dimensionless.
G is a dimensional number. It's the Reynolds number. Is the in electrodynamics will be the fine structure constant.
So that's set by some inherent properties of the system? Or?
Yes, I will show it. I think next slide I will tell you what G is. There was another question. Yes.
So depending on the total size of the system, you can, the coherence length is different, right?
Well, actually, what matters is the ratio. The ratio is dictated by... G is also a dimensionless number. Okay.
Yeah, but say for turbulence, you said if you have a
Yes.
then you can use Navier-Stokes under 30 nanometers. How
Good,
is it that
good
you-
point. No, you're right. You're right. There is a flaw here.
More.
No, you're absolutely right. There is a flaw because, as I will, not a flaw, but I mean, it's less simple than that. In the sense that when I will define G for turbulence, G will itself fill L. So this is just, I mean, how would I say? This is just to convey the notion that here the tension is mostly on the coefficient, okay? All I wanted to show is that the coherence length, I mean, it's an interpolate between these two scales, and depending on the strength of the nonlinear interaction, you can bring it closer and closer to microscopic, okay? Independently of whether this is 1 meter, 10 meters, or 1 kilometer, okay? But this is not, strictly speaking, this is not strictly true because G itself, in some cases, can depend on the size of the problem, okay? But this will not affect the exponent, though.
But in the lower equation, then the microscopic length scale can in some cases.
Yes, sorry. Yes, but if you, I think if you now divide this by L, what you get, I think now you get a little bit tangled, but if you take L coherence over capital L, then this ratio is related only, again, it's always a relation between ratios of coherence versus global or microscopic versus global. That's all I meant. I'm not sure I'm answering this question. Maybe it becomes clearer. Let me go to the next one and give you a specific example. Maybe it becomes clearer.
Sorry,
Yes?
I don't know when you plan to have a break, but it's been almost an hour, over an hour.
As for myself, I would go on, but it depends on the owners. I'm pretty much behind schedule, but that's fine. You want to take a break?
Well, let's see how the audience feels. If you find a break useful, about 5 or 10 minutes, or you want to continue?
Break. Okay.
Yeah, let's
Okay.
take a 5-minute break.
A quick announcement. I think this break worked out well. So from tomorrow we will have coffee and pastries at the break. So you can stay around. And we'll go to the next hour
Okay.
of sour lectures.
Thank you, Tim. So,
And please keep up the discussion. I mean, this is
yeah.
supposed
Please,
to be
please. Please interrupt me anytime. So, let's keep going with this notion of coherence length. So the question is, how big is G? Okay, and well, where did I put my? Which ties in with your question. Now, once again, turbulence or fluid dynamics more generally, and let's now be more specific. G is kind of abstract notion. Let's now put some flesh into the bones. For turbulence, G is the most typical G is called Reynolds number, and the Reynolds number is basically a measure. As remember, I told you this G is always a measure of competition. Okay, so it's a ratio of some typical time of length scales.
Can you please just define all the symbols for us?
Yes.
Except for the derivatives.
Okay. DDT, U is a fluid velocity. I didn't bother putting vectors here, but this is normally a vector field. This is U grad U, is the inertial fluid moving its own momentum. That one.
The term you were showing.
That's the term I was showing. This is the term I mentioned but didn't specify is the viscosity. So this is the kinematic viscosity of the fluid, centimeter square per second typically, and please notice that this acts upon a second order derivative, okay? Whereas this is first order. That makes a big difference. And this grad P, this is a pressure, and this is the fluid density. As I said before, I will not be dealing much with compressible flows, so for us, rho is basically dummy, is a constant for incompressible flows. Incompressible means that basically the Mach number, so the ratio of the fluid speed to the sound speed is small. Say, in a car is about 0.1. In airliner, this would be 0.8, and so rho would be a dynamic field. But as far as we are concerned, we can consider rho constant. So we focus our attention on the Reynolds number, which is the ratio of advection to diffusion, or dissipation, if you want. This term to this term. Now, if you take this dimensionally, just replace grad with 1 over a length, what you get is just u, so the fluid speed. I should have used a capital U because this is the global speed of the fluid, okay? At the scale, the fluid speed at scale L, L is the global size, over viscosity. Now, I already told you, but maybe it's still worth asking, what would you expect for this number in ordinary, really very ordinary life? So in a car, well, I think I already told you, but maybe you didn't get me. If I give you 3 numbers, say 0.1, 100, and 10 million, which one would you pick up? I already told you, but of course it's not easy. Don't do that calculation because otherwise it's too easy.
What was the question exactly?
The question is, I give you a car,
The car. Yes.
standard cruise at speed, and you have 3 possible answers. What is the Reynolds number of the car? I give you 3 possibilities. 0.1, 100, and 10 million. So small number, moderate number, huge number. I'm just talking a car, simple daily life.
Well, the viscosity, I guess, is about 10 to the minus 5.
You're doing the calculation.
So it's closer to 10 to the 7.
So it's 10 to the 7.
Right,
Okay.
I mean, you have the concept down there also. Right?
And the concept, well, but this concept is again not easily, I mean, it is like that, but it's not often spelled out. So the turbulence is a strongly interacting theory because basically advection versus diffusion is essentially like measuring. The Reynolds number is how many molecular mean free paths it takes to cover the whole car. So it's an unfair number because you're measuring macroscopic quantities versus microscopic quantities. This depends on the atomic property. The viscosity of the fluid is the mean free path times the thermal speed. So you're down in the second level of the hierarchy. You are kinetic theory, if not atomistics, whereas here you are talking quantities which are macroscopic. So the reason why this is so big is because, in fact, you're talking 2 different levels of the hierarchy. But yet, this doesn't change the fact that this number is the relevant number. If you now rewrite this equation in dimensionless unit, you will find the Reynolds number, 1 over the Reynolds number in front of the dissipation. Or, if you want, you find the Reynolds number in front of the advection. So that means that advection is typically much, 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 much stronger than dissipation. And that's, I would say, the bottom line. In the macroscopic world, inertia is fundamental. Inertia is really what drives motion in the macroscopic world, which is by no means true in the nanoscopic world. In the nanoscopic world, noise is important. And in fact, the mechanism is completely different. But macroscopic objects move essentially because inertia is really strong. Yes? Hi, Bruce. You're right, because I cheated a little bit in the sense, no, I didn't cheat. This is the Knudsen number. Bruce is right. But I am assuming that the Mach number, I would need, okay. I would need the blackboard. But this is the Knudsen number, but the Reynolds is the Knudsen number times the Mach number, and I assume that the Mach number is 0.1, so it's a number of order 1. Okay? So, but you're right. I mean, strictly speaking, the Reynolds number is, well, I would have to define yet another number, but this is not complete. This is not formally correct in the sense that there is this ratio has to be multiplied or divided, now I don't remember, by the Mach number. But I'm assuming that the Mach number is a number order 1. Say, could be 0.2, 0.3, but it will not change the fact that I'm measuring a macroscopic length in units of a microscopic length. This was the message. It's not equal. But you're of course right. I mean, I would have to introduce the Knudsen number, which at this point it really doesn't. But the relation is like this, I think. Okay? And I assume that Mach is order 1. That's all I did. But just to say that we have really a strongly interacting theory because, and here I have put down some numbers, which are representative of the application. I mean, in turbulence, the coherence length is called Kolmogorov length, and we can derive it rather quickly, that it scales like the total length versus Reynolds power 3 to 4, what I call the penetration index before. Now, consider that how many degrees of freedom do you have in your application? That's the question you ask when you want to do multi-scale. I forgot the sub-index k, so this is Lk. Well, in a box of size L, if the smallest possible length, the coherence length is Lk, you have capital L over small l cubed, and due to this dependence, you have Reynolds power 9 to 4 degrees of freedom. Storage. Then, of course, you have to integrate this, your equation for given a time span, which we can assume will be proportional to L, so you will get yet another 3/4, so the computational work will be Reynolds cube. But let's stay with storage alone. As I said before, you do the calculation for a simple water faucet in your kitchen, Reynolds is 10 to 4, about 1 billion degrees of freedom. 1 billion, in fact, not degrees of freedom, so that's almost enough to saturate a powerful machine, and the work is 10 to 12 floating point operation, at least with a big prefactoring phone. So this is, I think, basically the borderline of what you can do today. A car, 10 to 6, possibly 10 to 7, degrees of freedom, 10 to 14, 10 to 16, you cannot simulate a car. Simulate, I mean, you cannot put your grid resolution at the level of the Kolmogorov length. The Kolmogorov length is too small. And from there on, it's getting worse and worse. In geophysics, typically you have 10 to 9. Astro was putting 10 to 10. I've just learned can be 10 to 12. You can do the calculation. So degrees of freedom, storage, Reynolds 9 to 4. Work, I didn't write here, Reynolds cube. You cannot live with such a fast-growing complexity. So basically, you have to invent different ways of approaching the problem. You cannot just, some people call it brute force. I don't like the word brute force in simulation. Good simulation is never brute force, but I mean, I would call it direct simulation. Direct means that you can resolve up to the coherence length. So for turbines, you can resolve a faucet. A car is just too much. So what do you do? This,
when you're estimating the work it takes, you are having an assumption on what the time resolution will be.
You're right. No, I just took the time, space and time, I treat them on the same footing, which is not necessarily accurate. You're right. But here I'm just providing, you know, the flavor of it. Basically, all what I'm saying here could be corrected and amended. Never forget, I just mentioned guidelines. We are talking difficult problems here. So if you dive into the difficult problems, you have to, amend the general state. So this is a pretty compact slide, which I borrowed from Steve Orsag for turbulence, but I think it really applies to general philosophy of multiscale, which I like to make a kind of bold statement. The multiscale is just a way of implementing the least computing strategy. Paradoxically, computational physics, the goal of computational physics is to do the least amount of computation that you can possibly do, right? So, and I wonder whether there is a sort of least computing principle in nature. That would be an interesting question. I think so. But anyway, generally speaking, so we have now it's called another name again. I apologize for that. It's always the same thing. Sometimes it's called dissipation length because that's where the coherence length is where dissipation takes over. But it's always the same object. Coherence length, Kolmogorov scale for turbulence or dissipation length. So capital L, small l, we know, and here you have the spectrum. Now you have two possibilities. Either you do Muscles, full computing, all the way down, okay? Which we just have seen you cannot do unless you have, for a car this is not doable. Or you are smart enough that you don't need to compute anything and you have a theory which covers it all. That's very hardly the case in this kind of problems. So you have to live in between, and that's what we were discussing before. Typically, you are given a certain amount of computational resolution, which I call delta, and this delta will be larger than LD. So you can compute up to here. And I'm sorry about the colors, which is this point may be confusing to you, because the green part is still macroscopic. Okay, so it's not microscopic. I should have used different colors. But this is the part I cannot resolve. In other words, if I can use it. Oh. I hope you can see. I have grand L, small l, but my computer only goes up to delta. So delta is just too big for the coherence length. I cannot resolve it. That's where the modeling starts. And this modeling in turbulence is called large eddy simulation, but I think this is a general philosophy. What you cannot compute, you have to model. With theory, typically with theory. In fact, I would say multiscale is really a beautiful blend of simulation and theory. You have to know the theory. You have to know your damned physics if you want to do a good job. Not that you just blindly use computer. You just do disaster if you do that. So what you do, you compute all eddies. Eddies means degrees of freedom in general. Okay? For turbulence, they are called eddies, but any nonlinear field theory has its own quanta, if you want. Okay? Elementary excitation. Larger than the grid size are computed, so you compute up to here, and the rest you model. The scope of multiscale, or any smart kind of simulation, is to compute the least amount of eddies that you can. So if you have a good theoretical model, or you have, as we've seen, microscopic case, you will merge a macro model with a micro model, in which case you are trying to push, assuming that the macro model is less expensive, you would try to make delta, you would try to push, in fact, your grid size as down as possible, and there you want to connect to the microscopic model. But the point I want to make is that you always have to play with this quantity, given your grid size, in such a way that you compute the least amount of degrees of freedom, the least significant amount of degrees of freedom that you have in your problem. And for turbulence, this is called large eddy. So, but I don't know why I put this here. Ah, yes, because as I was saying, now I'm using very much turbulence as an example, but please appreciate that nature really likes huge gaps, and I think turbulence is one case, but in chemistry, biology, you have situation where the gap is much broader. In fact, we have energy, and there basically the driver is the Arrhenius. You all know that mild changes in temperature can turn a slow reaction to a very fast one. You go from picoseconds to minutes to centuries just by changing the temperature over a moderate range. That is due to this non-analytic dependence of the relaxation rates on the temperature. So here you develop monster gaps. Complex materials, or even glasses, are even worse. Here there is a nasty interaction between the fast and slow degrees of freedom, so that you develop relaxation rate of this kind of singular behavior. And you know the famous Greek said, I think, pantarei, everything flows, because even solids flow, except that they flow in such a long time scale that you don't realize it. And this is because there are relaxation times which are extremely, extremely huge. And I think even the famous mass hierarchy problem in high energy physics is essential. The mass is basically a relaxation frequency too. So its mass is energy, and energy is the inverse of the frequency. So I think eventually even the famous mass hierarchy problem can be boiled down to a multiscale problem. For sure it is. I mean, the question is which equation you use there. But just to say that the fact that the nature develops huge gaps is really a very general one. So much for multiscale. As I said, we could discuss hours and hours of the various specific problems, but let me turn, I was promising three things: multiscale, physics, and level. Multiphysics is possibly, sometimes it's just, they are used as a byword for multiscale, but it really isn't. Multiphysics means that you have multiple concurrent phenomena, okay, and they may or may not be on different scales. You find even commercial software where they promise that you can do airflow and take into account the temperature, which is a separate phenomenon. Heat transfer is different from mass transfer or momentum transfer. And you can you typically have a set of partial differential equations, all nested together, which describe the evolution of different fields. Typically, they do act on different scales, but not necessarily so. And again, I think I've already mentioned this. I think a typical instance of multiphysics is advection-diffusion reaction. So this is the concentration of, say, some pollutant or temperature. U grad C is, again, the convective transport. D is the mass diffusivity. You put a droplet of ink, and the ink starts to spread out. So this is diffusion. And eventually, you have reactant and products, and so you have chemical reaction which transforms species into different species on a time scale TR, which is the reaction time. And here again, you can define your dimensionless quantity. So you have an advective time, which is the length over the speed, a diffusion time, which is length square over the diffusion coefficient, and the reactive time scale. The typical number here is the Damm-Köhler, which is diffusion over reaction. And you can immediately check that when Damm-Köhler goes to 0, in fact, the G here is the inverse of Damm-Köhler. So small Damm-Köhler means strong interaction. So chemistry is very fast, and what happens in a thin flame? Very hard to, that's the difficult problem for computational, because the flame becomes so thin that you have to put a lot of resolution in the calculation. On the other extreme, a more quiescent framework is when the Damm-Köhler gets to infinity, which means that the chemistry is much slower than mechanics, so the chemistry always takes place in a mechanically stable situation. That's the case of slow reactors. But the point I want to make is that due to the Arrhenius dependence on temperature, you can really move huge steps between Damm-Köhler 0 and infinity, and this is the case where temperature is really calling the shots.
So give us a sense of where temperature enters in these quantities that you define, D and...
Temperature, essentially, is the chemical reaction rate.
What about the diffusion?
The diffusion is much, I think diffusion eventually depends on the square root of the temperature. That depends whether you have an ideal gas or a liquid, or it can be even inverse of the temperature in a plasma. But it's certainly always algebraic and with small exponent, whereas Arrhenius is non-analytic.
But in a situation where you have activated motion responsible for diffusion, that's also...
Ah, you're right. In solids, you mean. Okay, sorry. Yes, yes. No, you're right. The situation I'm thinking of is... for instance, in a flame, so you have, in a reactor, you have some reactant R, which comes into a contact with, say, A, which comes into contact with B, and these will be the space distribution of the concentration. So the situation I'm referring to is where you develop a reaction layer whose, it's probably written there, yes, the reaction layer, let me call it delta, such that the diffusion times the reaction rate is delta squared. Okay? So that means that if chemistry is very fast, so the reaction is very fast, everything takes place in a very small, and this is the coherence length of the problem. Okay? But I'm referring to a gas situation. You're right. In solid state, you have a situation where diffusion is also activated. To me, the only activated process here is tau R, which is exp minus some energy barrier for going from A to B. Something like this. So A to B into products. Something else. So the reaction will bring me from here to here, and I have a potential energy barrier. So this dependence can be wild, but as I was saying before, from the point of view of the penetration index, as I called in the previous lecture, this is less penetrating than turbulence, just because of this, essentially, this L square over D. But I mean, advection, diffusion, reaction problem turbulent combustion is one of the most horrible problems in computational physics. It's really a nightmare, because you have flamelets everywhere, so you have the complication of turbulence and fast chemistry at a time. I think it's one of the most complex applications in computational physics I know of. Because, of course, as an example of multiphysics, you have an equation for C, but you should couple this equation of C with an equation for the temperature and with an equation for the flow. So that becomes multiphysics and multiscale at a time. But formally, I would say that here we are in a framework which is relatively well studied by the applied mathematician, because, I mean, this is perhaps too formal, but the point I wanted to make is that you build up a sort of superset of partial differential equations. So psi 1 would be, say, concentration, psi 2 would be temperature, and you can have many species. So you build up a state system which is very high dimensional. So you have very many PDEs, and this is just an abstract notation. I write it in sort of evolutionary form. So you have 1, 1, 1, 2, 1, P, where capital P is the number of processes which you have in the game. And this, please I don't want to fool you, this doesn't need to be a linear operator. This is generally non-linear operator. So the big question here is to sort out, formally it's very easy. Say, okay, my state vector at time t is just x pel t, but this x pel t is a nightmare. And essentially this depends on the spectrum of the time scale. Suppose you have just two mechanisms. So this is the time scale at a given length scale, L1, L2, L3. So if A and B, say reaction and diffusion, are well separated, the task is easy. But what typically happens is that as you move up or down in scale, the spectrum opens up, say, because of temperature, and eventually they overlap, and there where they overlap, you have multiphysics and multiscale at a time. So that's the typical scenario, qualitative. So this is easy, this is tough, because you have to solve from year to year, and not just from year to year plus from year to year. So this is much more complex.
So different color means different physics, right?
Yes, right. This is chromodynamics. I should have had 3, so we have the 3 quarks. But that's really what happens. I mean, that is a typical scenario. This is a cartoon, but that's exact. So this situation is easy. You do some spectral analysis. You have some nice eigenvalue solvers. And if the eigenvalues are well separated, any numerical method would do a good job for you. Try to do eigenvalue decomposition here.
This is very trivial, and you can take
Now, what I'm saying is very trivial, too.
I'm just curious why you represented the green on top as transparent. What was your thinking behind that? You made a decision. No, I'm not confronting you. I want to understand.
I'm bad at PowerPoint.
No. So it's just.
That's the only.
You're not saying.
This was, it was not planned.
Okay, fine.
It's just that I'm too bad at PowerPoint. Eventually, if I have to make a pick now, I would say that I prefer this than this because the blue should lie below. Blue is my time scale, and I want the physics on top of the time. So I would prefer this if I had a pick. This is just because I was too sloppy or not capable.
No, I just thought, that you were saying something that we should understand.
No. Sorry. All I want to say is that this separated phenomena can blow just because of, say, temperature, so as a result of interaction, and that eventually overlap. There where they overlap, you are in trouble. Multi-level is nice, although I know little about it. And I think there is really, that's probably of the 3 M's is the one which is lagging most behind. But essentially, at least to my perception, multi-level is the following. It's just having different hats, the same person wearing different hats. As I said, some fluids are typically represented as continuum fields, because this is perceived as being the most economical representation. But fluids are made of molecules. So from time to time, you may want to represent fluids as a collection of molecules, and it is still the same fluid. So it is the same person wearing 2 different hats or jackets. And there is very nice what I call the chimera strategy, right? So the chimera, is changing. It's not changing phase. What it is? It's 2 different animals in a single body, right? Actually, chimera is only 2, but eventually you have a multi-chimera. And there are already some interesting applications. The one I know are in Max Planck's group of Kurt Kramer, where the mathematical representation of the same physical physical system does not need to stay the same all along. It can change from place to place and time to time, depending on the actual demand of physical fidelity. In practical words, the example I was exposed to by Kurt Kramer, you have a polymer, I don't have the picture here. You have a polymer who has to get close to a surface where there is a catalytic reaction taking place. When the polymer, by the time, during, the landing process, you really don't need to know about the chemical specificity of the polymer. What do you care? It has only to move, and it can be any polymer. It is only by the time it touches and gets in touch with the chemical surface that he has to unveil his identity, because their chemical specificity matters. So I see a very interesting trend, and I'm just too jealous that I didn't do anything in that respect, where people change the representation during the same simulation. It's beautiful. Typically what I saw is that you have just, and we should do that ourselves, in fact. Typical polymer are represented as, anonymous objects from the chemical point of view, but then where they get in touch with the sensitive region of space and time, then they reveal their identity. And I think this strategy is extremely powerful, and I suspect we will see more and more of this for the coming years. But so far, this kind of multi-level facilities or tools are, I think, pretty much in their infancy, very much so. Much more infancy, less developed than multi-scale and multi-physics. Here we are. Yes?
In this perspective, usually, when you, for example, use molecular dynamics, you use mechanical forces. You go one level up.
So which one, Simona?
Say when you use plain molecular dynamics,
yeah.
atoms and molecules,
yeah.
then you use mechanical forces. If you want to go one level above, you may use effective forces, which is basically free energy.
Right.
If you want to do that step, you need to employ equilibrium conditions, so equilibrium sensitivity of the chemical. In more general terms, you don't have that help. So
I don't know, Simona. I really don't know. I think that's an interesting point. The thing I saw is the following. It's basically, we can really refer to ourselves. I think there is nothing wrong. This is a glorious thing we are doing here. Simone should get the credit, team, and I'm trying to help myself. And I think that really is typical of what one could do with multi-level. What we are doing here is a biopolymer, which we call DNA, but in fact it's not DNA, because this polymer has kind of generic interaction. And of course we want to know how this polymer gets across a hole in, this could be a cellular membrane. And what we are doing so far, this is plain molecular dynamics. So that's the level that Simone was referring to, okay?
Can you just say what you're applying? We can see the beads of the polymer, but what are the payloads?
These are essentially beads of the polymer. And what they're plotting is this is a measured interaction with the solvent. Let me set this apart for a while. That's something we are very proud of, but I will comment on that later. Let's forget now about the red field. And this is just biopolymer where the interaction bead to bead are just molecular dynamics. Okay, that's assume. And I think as far as the polymer is away from the membrane, this I think is perfectly fine. Now, when it gets in, it could well be that the way it's interacting with the nanopore really depends on the chemical content of the polymer. And for the time being, we are just ignoring it. What we should do, and what we'll hopefully do for the future, once we are inside here, we open up the polymer, and instead of one bead, which is position and velocity, maybe we can blow it up into a structure of several molecules. Would still be maybe molecular dynamics, classical, but maybe we open up the structure of the base pair. That would be the dream. So you see what I mean? So that would be a simulation in which you have to arrange your data structures in such a way that when you get there, you have somehow to expand your representation. And I think that what Simone was pointing out, that, and what I was in fact giving this talk about 6 months ago in the StatMephys conference, and very boldly saying, now we are using BlueGene, which we are very proud of. And again, I should acknowledge another person in the audience, which is Joy Sirkar. We are very proud of what we are doing with BlueGene here. And since we can now move polymers which are almost as long as the real experimental polymers, we can open up the polymer and give chemical specificity. Very bold statement, very proud. Then a guy stands up in the audience from Kurt Kramer's group and said, wait a minute. How do you, and he raised exactly the question that Simone raised, how do you map your anonymous bid into, say, a base pair representations? It's not obvious how to do that. And I think that's the typical case where you need physical insight. Frankly speaking, I don't have a clue. Maybe Simone does, but sorry. How do we know, Simone, that we can go from year to year using equilibrium notions? I would not say that we can, but I don't know. But going from year to year is a conceptual problem in the course of a dynamic simulation. So it's not a textbook situation. We have to think about it. It's a beautiful problem. But we have not done it. I mean, we would be in a perfect, I think our situation is just perfect for multi-level in this respect, but it's a lot of work. Hope some in the audience would be.
So I was going to say that in astrophysics we do this, but only for post-processing, because the timescales are very different. So would that not be an issue in this case, where you suddenly turn on new physics where the timescales are dramatically different and you slow down the computation?
Yes, but there are techniques, and I hope I can give you at least the smell of it, where in fact, it's called slow manifold techniques, where in fact, sometimes the fast degrees of freedom get enslaved to the slow ones. It's so just like having, and so you don't, how can I say? And so you don't track the fast scales, you just assume that they are enslaved to the large ones, so you move them on top of the large scales in large steps. And only from time to time you resolve the fine scale. This is confusing, I understand. But all I'm saying is that there is certainly a time scale issue, but there are also tricks, physics-based tricks, which you may or may not be allowed to apply, such that you don't need to track explicitly the fast time scale. If your physics forces to do so, there is nothing you can do. This is an irreducible problem.
Does that make it basically post-processing, but just doing it on the fly?
Well, post-processing on the fly is what we call concurrent computing. And I think it's, of course, is a quantum leap in complexity. I really don't know how to do that, frankly. But I know for sure that's the way. Maybe our kids, or maybe the kids of our kids will be doing that for sure. I mean, so we are preparing the ground.
Is this akin to assuming that the small scales are always in equilibrium with the large scales?
That's, by and large, this is the bottom line, yes. And whether or not you can do that, it really depends on your problem. But I would love to give a try at this. I mean, for sure you are improving on what you're doing now. It's technically complicated. I mean, you cannot do that, overnight. It would be a beautiful PhD thesis, let me say. But again, I may be boring. I'm insisting these are just general ideas. I mean, details are always tough to be worked out.
But there are also deeper issues having to do with entropy and how much you lose, and what's the definition of temperature now? Or
Yeah.
if you jump between scales, is that right? Or?
I think so, yeah. Strictly speaking, for sure it is. I think for this problem, Tim, we would be safe. I mean, because we know that, like in ion channels, I mean, the way biopolymers go through pores really depends on the interaction with the pore walls. So here we should really give some identity to our molecules. And that would be that, for instance, instead of having just position and velocity, you expand your bead into several molecules. And that will be already a better representation, even though from the fundamental point of view, maybe there are flaws in the description. But I think nonetheless it will be a progress. Frankly speaking, the question that Simone raised, who has the answer about this question?
I think out of equilibrium there is no answer for sure. Even if you have a local equilibrium, you are in trouble. If you have global equilibrium, then you can apply.
But you never have global equilibrium in driven situations.
In this case, you have no equilibrium at all. Only if you have a very slow process that you can apply.
In a way, I don't want to say too big words, but I think it's really a very deep issue. I mean, we are used to the idea that if you're clever enough, sooner or later you find the right equations for your problem. I mean, on paper and pencil, but sometimes I think you just have to simulate to know what happens. And, well, I don't know. I mean, it's, I shouldn't really go into a ground which I don't know, but enough of. But I think that, are we sure that there is a general theory, a local thermodynamics, call it whatever you want, which gives a general prescription on how to go from year to year out of equilibrium? It's not obvious that there exists such a theory. Or at least that it can be formalized in equations, other than the equation of this level coupled to the equation of this level. This you know, and that's exactly the spirit of multiscale. What you're referring to, Simone, is a kind of very sophisticated constitutive relation. That's what you're looking for. Sometimes they don't exist, period. All you have to do is to couple this and that in a correct way. But the equation you're using are the equation for this level and the equation for this level, period. But, I mean, that's getting too philosophical. But I think for this problem, it would be a wonderful test ground. Now, there are even more complicated things, and that, again, to refer to the activity, our activity here within the IIC, we are supposed to produce hemodynamics results. And hemodynamics, like most real-life problems, is a jungle of scales. I mean, you can go from the full human body size, so the arterial tree, which is 1 meter or so. Arteries are the order of centimeters, and if you have a clinical problem, you have to say, understand how drugs are, effective in terms of healing sicknesses. Very often, when you talk to medical doctors, they tell you, okay, you have the genetic information. We know that this drug, on the chemical basis, is the best one we have. But when you do the clinical test, you find that the best performance is not the best genetic performance. Why that? Well, because, I mean, in order to get to the I mean, you have to take into account the environment where you are administering the drug, so delivering the drug, and so you have arteries, capillaries, and you have a lot of mechanisms. Like, for instance, take inflammation is horribly complicated. This is a leukocyte, and this is rolling over. You have adhesion processes, deformation, and then eventually the leukocyte will penetrate into the tissue. And I mean, just describing a process like this is just a dream many years ahead of us. Well, I mean, up to here, I think we can do. This we can do, right? Simone is basically.
You think without any other stuff being in there, you can do the first 2 steps? I mean, we're not seeing anything else in the artery. I mean, there's so much else going on. There's so many other things present.
What do you mean, here inside?
Yeah.
Oh, yeah, sure. I mean.
So you don't even, you don't pay attention to that. You just can't. It's just
Well, look, if I could do this, I would be very happy. I mean, so far what we can do is this. I mean, moving solid objects or eventually deformable object within a capillary, which is non-trivial, really. I mean, if you talk to the guys who do a blood flow simulation, they tell you 3D arteries. I think, Jonas, you have done that in Geneva?
Yeah, I haven't done it, but
yeah. But I think people agree that doing just the flow calculation is done. I mean, people know how to do it and know how to do it fast. And we do it very fast ourselves, I mean, on the Blue Gene. Now, adding this further level of complexity, which is to say moving deformable object within the flow, is already frontier. We are getting there. We will do a good job. I'm pretty positive on that.
There's a flow there, too.
There is a flow here.
Which is not shown, yes.
which is not shown.
Yes. Right.
That's just work for you.
But I mean, this is a very naive question, but there's just so many other cells present.
Oh, yeah, yeah.
And are you taking that? Is there any way to take that into account?
Yes, there are ways, but I mean the problem becomes really unaffordable. I mean. No, the techniques I think here are more or less. I think we don't have. I mean, deep fundamental questions like the previous one, I guess. Of course, you have to gather knowledge, medical knowledge, physical, chemical knowledge about these processes. But I think we would know. We have a pretty good idea on how we would model that. Just it is very complicated. So what is this? Yeah. So what I was saying before, we are almost done in the sense that bridging the gap, so constitutive relation is the way people bridge, in fact, from micro to macro. And these are the constitutive relations I already mentioned. I think you are all used to that. So if I have a mass flux, I say that the mass flux is proportional to the gradient density of the mass density times a constant, which might be a tensor eventually, which collects, in fact, all the information on the micro world. Same goes for momentum, same goes for heat, and these are near equilibrium, whereas Walter Kohn wrote a nice paper saying that nature, near equilibrium nature is short-sighted. So all the microscopic world, it can be boiled down to some effective coefficients. Far from equilibrium, nature puts its glasses on. And constitutive relation, and I mean, you have very clear symptoms of that. Constitutive relation becomes unwieldy. Of course, you can generalize and say that they are tensor, they are non-linear, they are non-local, they are non-Markov, they are non-everything. But at that point, what's the use of them? I mean, you're clearly on the wrong path. So mathematics, and this is, and really it's back on you even mathematically, because mathematically this problem are ill-posed, the boundary condition become a nightmare. So I think this reveals, is essentially reflecting the fact that you are not approaching the problem from the right side. So constitutive relations are invaluable, but they are not the panacea. And is multiscale the panacea? I don't know, but certainly it's a more powerful way. It's a way of going beyond constitutive relation. It's perhaps less elegant in certain respects, because I don't think maybe we will be able to formalize a multiscale framework. I think the heterogeneous multiscale method is a serious attempt in that direction. But even if you don't, clearly by computer simulation, you can go beyond the constitutive relation. And so the question is how to do that effectively and possibly without violating any basic physical principle. I think this is the end of the first lecture, which expanded by a factor of 2, but we don't care. It's much better if we interact. So let's see if there is anything new I need to say. So yeah, essentially multi-scale, triple M is needed whenever cross-correlation are key, and this which is certainly true for complex systems far from equilibrium. I think, let me see, I think you have been exposed to all of this. And really, I don't like the notion of computing as brute force, because behind good computing, there is always interesting, and you have to absorb the theory, the physics. And if you don't absorb, if you don't master the physics, you will never be able to do the right mix and to achieve what I call the least computing strategy. So multiscale is about least computing. So all of this has already been said, so I think I can switch. How much time do we have, Tim? Fine. So we will, I really don't care. I mean, as long as you don't. I mean, so we'll probably have half of it, but fine. Maybe we can continue in the future.